what is the work done? Well, hopefully you'll remember, or if not, and you're panicking, go to the first page. Work is force times displacement. With the dot product, the formula has a dot in it, so you can do a dot product. If I gave you a force and a lever arm, and I said find the torque, well, torque, the formula is a cross product.
Okay.
In terms of, is there some inherent, given the situation, to use dot or cross? Well, dot products produce scalars, so, and cross products produce vectors, or pseudovectors for the purists. Yeah, I'm not quite sure I can really come up with something other than just the way things are defined.
Okay.
So, the dotted lines that you drew, is that technically coming this way?
No, that was not the intent.
Okay.
All right, so I have the two vectors and I want to figure out the angle between them.
Okay.
So in essence, if you ignore the axes,
And just tip to
and what I was hoping to do is, if you extend that,
that way.
I'm trying to figure out that angle there, I would do 5 times the sine of that angle to get this.
Okay. So then,
But if I know that is 103 degrees, that would be whatever's left over. But sine of theta is equal to sine of 180 minus theta. So the sine of this angle and the sine of that angle are the same.
so then when we're looking at 30 sine 103 for our K hat, that is literally like 30 sine.
Yeah, whatever number that is in the k-hat direction, that is the answer.
Okay.
Right now, it's a math problem. I haven't given any units. I've given no context. It's just a straight up math problem.
Okay.
Ritika?
So when we do I hat dot I hat, we end up with 1
Yes,
because they're unit vectors.
yes.
Why don't we, aren't these unit vectors as well?
They are unit vectors as well, but the part of it is the dot product multiplies parallel parts. So I hat is parallel with itself, so you're multiplying 1 times 1. Cross products, you're multiplying perpendicular parts.
Right.
And I hat is not perpendicular at all with itself. If you drew down 2 I hat vectors using the same coordinate system, they would have to point in the same direction.
But J hat cross K hat should be 1, right?
Well, it's a vector product, so the magnitude would be 1 and the direction would be, J hat cross K hat would be in the I hat direction.
Okay. But the magnitude is 1.
Magnitude is 1, yes.
Okay.
I think we're ready to combine a couple things here. Now let's do a simple problem first, and then we'll start combining stuff. We are now going to get rid of the frictionless requirement of the ideal root. We are still going to assume some ideal. We're going to assume no slipping. But the tension in the string is no longer a constant. Let's make that a 3 kilogram mass and a 5 kilogram mass. And I want to know what is the acceleration of the masses. Force diagram, pulleys being held up by something. So I've got my 3 kilogram mass here, I've got the 5 kilogram mass here, I have rope, I have pulley, I have rope. Notice I'm treating the rope as 2 different ropes. That's because with friction in between them, wow. With friction in between them. With friction between the rope and the pulley, the tensions are not the same. And again, it's like two people are doing a tug of war, third person comes up and starts pulling on the rope in one direction or the other. You got your
No,
hand
no,
up?
no, no.
Okay. So, force diagram.
Weight is acting on both of them, on 3 and 4, I mean 3 and 5. And there's tension between their strings and the boxes.
I'm gonna call this FT3, 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 and same over here. And there's something holding it up. Usually it's a normal force, so I'll just do Y sub P for pulley.
Why is there tension on the top of the string? From the pulley and the string? Aren't the strings are connected?
The strings are connected, but the tension changes while it's touching the pulley.
Okay.
Why is the normal force acting upward?
I was sort of figuring, if I've got a pulley here and I have something pulling down on it, that there's got to be something holding it up, keeping it from falling. So I just figured that the axle was resting on the bottom part of some structure, which had to have been pushing up on it to keep it from falling.
So usually it's perpendicular to the surfaces of contact.
Yeah, so if we zoom in on that, let's see, so that's pulling down on the pulley, so that's the inner axle of the pulley, and then I've got, let's zoom in further. That's part of the pulley, and that's part of the structure holding it up.
Right.
So there's some contact from here to here.
Mhm.
There's gonna be a normal force pointing in all these directions, but the net normal force is gonna be close enough to up. Ultimately, this force right here is irrelevant. Unless we needed to figure out, is it something gonna break there, but that's not our purpose at the moment.
Friction?
Pardon?
I said friction.
Is there more? Yeah, there's friction involved here.
Okay.
If there were no friction, then these tensions would be the same, and the pulley wouldn't turn. Oh, I do need a mass of the pulley. 0.1 kilograms, and let's give it a radius of 0.5 meters. No, we're using 5 already, 0.6 meters. That's a big pulley. That's the diameter right there. All right, so direction of acceleration. Which way is the 5 kilogram mass going to accelerate?
Down.
Which way is 3 kilogram mass going to accelerate? They do have the same magnitude of acceleration because the rope's still not stretching. Which way will the pulley accelerate?
To the right,
Let's get that.
because I was thinking about how to talk about tires spinning. And if the thing is pulling this way, I was thinking from the radius, maybe going to the right.
So but the bottom's going to be going to the left, wouldn't it?
You do clockwise,
Pardon?
clockwise, instead of, or is that the same thing?
How do we express that? Clockwise acceleration, pardon?
Is it towards the room? Is that what you're asking for?
Right here.
Oh. Oh, shoot. Towards the board?
Into the board, yeah. So clockwise, counterclockwise, we're trying to get away from. So it's going to, if it starts at rest, it is gonna rotate that way. Acceleration would be into the board. So if I use this coordinate system here, it would be in the negative k hat direction.
It's just gonna be the X.
Pardon?
We're gonna use the X, like the into the circle X. We're gonna use that one. For the-
Yes,
okay.
yes. All right, so now we need to set up our coordinate system. On this one, which way do you want to, it's a one-dimensional problem down here. Which way do you want to make positive?
Down.
Over here,
Up.
and at the pulley?
Towards the.
The right is positive? Are you asking if up or down with the pulling?
Actually not asking up or down with the pulley.
Into the board?
Yeah, into the board I would recommend making positive. If you want to do the balance of forces here, you can, but ultimately, I don't really like E is going to be equal to the sum of these two. Do we need to decompose anything?
No.
All right, equations of motion. There'll be 3 equations of motion. I have 3 objects, each with 1 dimension of the equations.
FT3 minus W2 equals M3A.
All right, 1 down.
W5 minus FT5 equals M5.
All right. Obviously, I don't know either of those two tensions. I don't know acceleration. I have 3 unknowns there. I need a 3rd equation. And fortunately, we can do it. What is the rotational analog of Newton's second law?
The acceleration. The centripetal acceleration.
What?
The centripetal acceleration.
No, not a centripetal acceleration issue. We're dealing, it's centripetal acceleration, if we cared about some change in direction here, what we really care about the fact is the wheel is going to get faster and faster and spinning. So we're talking angular acceleration.
So,
Torque is equal to rotational inertia times acceleration. Or the,
Angular acceleration. So these are based upon F equals ma. When you get into the rotation, you're now dealing with tau equals I alpha. That. So our 3rd equation is going to be the torque about the pivot point is equal to the moment of inertia of the pulley times alpha. Well, if I'm looking at torque, I know torque is R cross F. I have 2 forces, actually I have 3 forces acting here, but this isn't doing, this exerts no torque about the central axis. Because it's like trying to open a door from pushing on the hinge. So I have basically torque from 3, actually 5 is going to try to rotate it that way, so I have torque from 5 minus the torque from 3 is equal to I alpha.
So all of the torques are acting in that direction?
Torque 5 is acting into the board, torque 3 is trying to rotate it the other way. Sorry, tension 3 is trying to rotate it the other way out of the board. So that's why I have the minus sign. Substitution, so I have FT3 minus M3G equals M3A.